Again, I want to make it clear to you I could prove all of these things if I wanted, but it would take a year's calculus course to do so. And I'd get myself all tangled up and flustered because I haven't done it since I was an undergraduate. So I can't remember it all. Actually, I can remember this. There it is. So again, we've got this split into 2 bits. There's no x here. This bit does the work. This bit ensures the area equals 1. It's called a normalization constant. Or a fiddle factor. The proper word is normalization constant, but really it's a fiddle factor to make the area add up to 1. And we'll see how that works right now. There's my standard Gaussian. Now what I'm going to do is just replace, I'm just going to replace that with sigma squared. This is going to fail. Oh, I've forgotten my 2. Oh. I've forgotten my 2. Let's start again with that one. I think I'm getting myself tangled up here. When you look at my formula's got a division by 2 here, and I'd forgotten that on this curve here because I should be dividing, inside the exponent I should be dividing by 2. And I've not done that. I should really have brackets there as well. There we go. So it makes it slightly wider. I would say in my defense that in my research I consider Gaussian distributions of complex numbers with real and imaginary parts. And if you do that, then the number 2 disappears. So I've always got this problem in my head that my teaching has got a factor of 2 and my research doesn't. So depending on what hat I've got on, I sometimes put the 2 in and sometimes don't. This is the correct form. Okay. So I can just change the standard deviation. I can say x squared, x minus mu squared over 2, and it doesn't know what mu is. So when I plot that, mu becomes 0. We go back to the standard Gaussian. Oops, mu becomes 1. We've gone over to a mean of 1, which is here. All I'm doing is typing out this equation here, but with different values in. Of course, here what I've got is sigma squared equals 1.
So can you just define mu again?
Mu was the mean.
Okay.
Mu was the mean value. It's just here. It's not a good picture because it's chopped off this bit off here, so it doesn't balance. But you can imagine. Mu is just the mean. You write it just mu like that, but it's u with a sort of tail on it. Okay, so now I'll put sigma in there. Just have a look at that, see how that works. So all I've done is type out the formula but with a sigma squared in, and it's going to fail because I haven't told it what sigma squared is. I've screwed up and I can see where, can anybody else see where I've screwed up? I've not, well, you can see the plus sign means it's waiting for something and it's waiting for a bracket. When this happens, don't panic, just close off lots of, vandalize it. Bonk. You see, and it says, all right, so what I should have done is close off this bracket here because it's e to the minus all this lot. You see, all I'm doing is typing out that equation there. I need to close that bracket there. And it'll still fail because I haven't told it what sigma squared is, what sigma is. Bonk. And this error here says object sigma not found because I haven't told it. So let's go through the simple case, which is sigma becomes 1. And there we're back to a mean of, the mean's mu, which is 1 still, but we've still got a standard deviation of 1. Now I can make it a bit wider. And it's rescaled and made it a lower, fatter distribution. But we've lost the first one, so I should have used points. I'll go back and do that one again. There's my plot. Oh, sigma equals 1. There's my standard Gaussian. Change sigma to be 2, and then instead of plot, if I go points, here we go. So basically what I've done, to go from this distribution to this distribution here, I've made it twice as wide because I'm scaling by 2, not 1. This is scaling, well, not scaling at all. So you can see it's got wider, and it's also got lower because it's got to have an area equal to 1. So this extra area here, and it's truncated, but that area there as well, will match this area here directly. And I can also change my mu as well. Where's my mu? -2, let's say. And this distribution here has got a mu of -2, but you can see I've missed most of it off. You can see if my x was larger, I could have coped with it. Okay. This is quite a mouthful and quite difficult to do, and there's quite a lot to go wrong, and this formula is quite complicated. We'll see as the course progresses that we'll need that formula because we're going to think about it. But it should come as no surprise to you that R can do all of this. What time is it? Got 20 minutes. R can do D norm in the same way that we've got D binom, we've got P binom, we've got R binom, and we've got Q binom, which is on the screencast. We've also got a sequence of normal variables or Gaussian variables. Just give it a minute to fire up. There it is. D norm. X is the horizontal axis. Mean, which sometimes you call it mu, sometimes you call it mean. Standard deviation, log equals false, which I'll not cover. It just returns the log of the density, that's all. So we've got a nice little help page here. These values here, when you look at the help page, this mean equals 0 tells it that the mean equals 0 unless I tell it something different, okay? So I can override that, but if I don't, it'll just pick up the mean from here and say mean equals 0 and standard deviation equals 1. So if I don't tell it any different, it will just plot the standard Gaussian. Or return standard Gaussian. So let's have a look at that. See how much easier it is to do this than this? And it's given me that nice thing there. But now I can start fooling around with it. I can go points. And it does mean equals 2. I'll do that again. What happened was that because my standard deviation was very small, it squeezed this value in here and it poked up at the top. But my axis, it didn't redraw the axis because I'm only putting points on an existing axis. So what I'm going to do now is go y lim equals from 0 to, let's say, 2. There you go. So now when I plot it, the limits of the y-axis I've told it don't just fit to the curve, go from 0 to 2 because I'm going to put some other stuff on it. Make it nice and visible. So instead of plot, I'm going to go points. Still not big enough, is it? You see, because I've squeezed it right in, it's poked its nose. There might even be another point even higher up there, which has gone off the top of the screen. Even so, you're getting the idea that we can, and I can change. So here you can see quite clearly that I can take this distribution here, I can squeeze it in, I can move it out, all within the context of my Gaussian distribution. Now, Gaussian distribution crops up over and over again. If you understand the Gaussian, everything's sweetness and light, and if you don't, the world is a very confusing place. So how do we link it to the binomial distribution? Well, I'm just going to tell you this, and then we'll have a workshop on it next week. And then I'll put it on the assessment as well. If x is distributed as a binomial with size n and probability p, then approximately x is distributed with a normal distribution with mean np standard deviation. This is an extraordinarily powerful result. If you do the third year course, whose name I've forgotten, we'll prove this, and it's quite a spectacular piece of reasoning, quite an unexpected result. It's something annoying to me that you specify, some people when they write a Gaussian specify the standard deviation, and sometimes people specify the variance. You'll remember the variance equals the standard deviation squared. So some people will write this same mathematical notion down like this. NP, comma, NP1 minus P, because that's the variance. You see, sometimes people include the square root. So if I said x was a normal distribution with mean 5, and let's just say that was 100, well, is that the mean or that standard deviation? It doesn't specify. Quite often you'll just see it in the literature saying, oh, it's n500. And I say, is that the mean or standard deviation? And there's nothing in there to tell me which one's which. It's crazy. Half of my time, I say, the real thing is the standard deviation because it's got the same units. If this is money, then that's the units of money. So the standard deviation is the width of the distribution, and the variance is just the square of it. The other half of my time, on a Wednesday, Thursday, and Friday, I say the variance is the real thing, and we'll see this later in the course. The variance is the real statistically important thing, and the standard deviation is just the square root of it that you do for children. So sometimes I think of the variance as the important thing, and sometimes I think of the standard deviation as the important thing. Basically, depending on what day of the week it is, basically. They're two different ways of looking at the same thing. And I will be confused. Sometimes I will not be clear whether I'm meaning standard deviation or variance, which is not good. Well, let's try that then. Let's have a look at it. If I look at our binom, here's some numbers. N equals 500, probability equals a third. My prediction is this, that the mean is 500, the mean is NP. You see, the mean is the number of trials times the probability of success. You'll observe that I'm going further than I went last lecture. Last lecture, all I asserted was that the mean was this and the standard deviation was that. And I didn't even define standard deviation particularly clearly. Now I'm saying something much stronger, much more powerful, much more useful, much more much closer to the truth, which is that not only is the mean and standard deviation, but also the shape of the curve matches my Gaussian curve. Even right out to the limits. The middle bit's easy, but even right out to the tails. It's a startlingly good approximation. So what I'm saying is that if I've got 500 trials with a probability of success of a third, these numbers here are approximately Gaussian with mean 500 over 3. And standard deviation (10). So let's have a look at that.
Where do you get to 2/3? 1 minus 1/3.
Yeah, it's 1 minus, oh, it's disappeared. Yeah, this 1 minus 1/3 is 2/3, which is this bit in the formula here. Which comes out to be the same. Okay? The histograms always suck. Comma. Of course, what's happening here is that I'm showing a large amount of variability because my sample size is so small. So I'm going to whack that up and have a nicer histogram. Let's do 1,000,000. That's more like it. There it is. This beautiful Gaussian curve. Isn't that beautiful? What I'm going to do now is open a new curve, which I think I go x11 to open a new curve. Yeah, there you go. Let me just type this. And then I'll take you through it. It's a little bit shonky because of the way I've done it. But here you'll see the binomial distribution. 500 trials, probability of success 1/3. There they are. And here is my histogram of the approximation, which is Gaussian with mean NP and standard deviation root n PQ. I've not put 1/3, I've just put a third over 3 there. And we can see that they match up quite nicely. So I can ask all sorts of questions now, such as this. If I have 500 trials, P equals 1/3 binomial, I can ask, what is the probability that the number of successes R exceeds, well, let's say 190? Okay. Now you'll remember the D binom, the P binom, the R binom and the Q binom functions. So we can just use what we're wanting to do is to use the Gaussian approximation, set up a Gaussian distribution here with the mean equal 500 over 3 and the standard deviation equals that. This value here is 190 and I need that area there. Okay. Let's go back to my help page. If I can find it. It's there. We're going to use this P norm here. P norm gives me this area here. P norm gives this. This is just revision. You should know this from 715. This area here. So in other words, P norm of, let's say, y equals the probability that my random variable is less than or equal to y. Okay, so P norm 190 gives the area to the left. So to calculate what I want, which is the area to the right, I need 1 minus that. And we can do that dead easily now. 190, because I want the area to the right of 190. %, and that's the area to the left. So P norm is giving me the area to the left of my curve, but I want the area to the right, which is 1 minus that. So I need to take 1 minus this answer here, which gives me 1.3%. So using this Gaussian approximation here allows me to answer very, very simply and very, very straightforwardly, and also in a way which is much easier to communicate. I can answer questions about extreme distributions of my binomial distribution. Of course, I'm not just going to let that stand. I'm just going to check that. Let me just do the other thing here. Okay, so what have I got here? Here's my approximate answer. It's approximate for two reasons. It's approximate because I'm using the Gaussian approximation. Yeah? And it's also an approximation because I'm not quite sure whether I include or not that 190 exactly. Because it's a whole number, do I include that as greater than 190 or not? There are ways to correct it, a continuity correction, but quite frankly, if you need it, it's the wrong technique. What's wrong with this technique here? This technique is deficient because it's got randomness in it. It's different from trial to trial. However, it is showing us that, what's my exact answer? There we go. It's a little bit under. Maybe the deficiency between this one and this one is caused by that exact probability of it being exactly equal to 190. Even so, it's quite a good approximation. So it's off for two reasons. First of all, three reasons. First of all, random variability. Second, the possibility that it's exactly equal to 190. Let's try that. Let's just try making it equal to 190 and see what happens. There you go. So you see this one's too small and this one's too big, and this one there is just in between. Maybe you should take half of those 190s. There are ways around this. So there you have it. Again, this is sort of revision from 715184, but a much more sophisticated way of looking at it. We've got formulas now, and now we can use this P norm function here. So, take-home messages. P norm. I'll write it here. P norm gives the area to the left of a point in a Gaussian distribution. We use this in conjunction with the Gaussian approximation to the binomial okay, because it's easy and straightforward to evaluate, and the binomial distribution is a dog. Right, I'm going to stop there, and I will see you next week in this tutorial where we'll use these with R. Okay?